Okay guys, welcome back to Heinzelvision. We're going to try this video tonight on my iPhone. Since I'm at home, I want to record something for you. And what I want to talk about in this video is the difference between conservative and non-conservative forces. So I want to leave you with two similar scenarios that are not quite the same, but they do have some properties in common. And we're going to take an object, a box, let's say, and we're going to put it through two separate motions. The first one, we're going to lift it up at a constant speed, so vertical motion. So it has some upward positive velocity. It'll experience some upward positive displacement due to that motion. And the second, we're going to move to the right across a table. And let's say it's a rough surface. So rough surface. Also at a constant speed. So it'll have some velocity to the right. It'll experience some displacement, delta x, to the right. So how are these two scenarios similar? Well, they're similar in that because of the fact that they're moving at a constant speed, there must be no net work going into the box itself. The delta K must be 0, because if it wasn't 0, then it would be speeding up or slowing down. So there must be no net work. But there are forces that are doing work in both situations. So let's look at the first one. If I'm lifting this up, there must be some upward applied force F sub A, just as if I'm pushing this to the right, there also must be some force to the right, F sub A. So there's some applied force that's doing positive work in both scenarios. So that applied force would be increasing the kinetic energy of each object, but for an opposing force doing negative work. So in this case, since it's a constant speed, the forces must be equal and opposite. We're in a state of dynamic equilibrium. And in the case of lifting, we're lifting against gravity. So in problem number 1 here, so FA does positive work, FA does positive work. So let's look at them side by side. And in scenario number 1 here, we have force of gravity, and that's doing negative work, since the object's displacing in the upward positive direction, and gravity is acting at 180-degree angle to the displacement, or in the opposite direction of the displacement. Now in this case, if I'm moving across a rough surface, there's going to be friction here, the force of friction, FFK. Excuse me, in terms of my stuffiness. But that FFK is doing negative work. So it seems like these scenarios are pretty similar. We have a force applied doing positive work, some resistant force to the motion doing negative work, but there's a dramatically different outcome based upon the energy transformation that each one of these objects experiences. So in the case of the box, as the box goes to a higher and higher level, we know that there's some potential energy stored. And the reason we know that is because if I lift the box and then let go of it, it's going to fall back down to the earth, and it's going to convert that stored energy back into kinetic energy. So we know when we do work to lift a box, we're storing some energy based upon the positioning of the box now in a gravitational field. What about this box? Where's that energy going? Well, in this case, when I push a box across a surface at a constant speed, there's no energy being stored. all the interaction between the box and the table is doing is creating vibrations in both of those objects that's increasing the thermal energy of both objects or the system. And this is a different kind of energy. This is not useful. Like, I can't, it's not useful in the sense that I can't get mechanical energy back. Right? Like, the friction just is spread out through the vibrations in the molecules of the objects. They heat up a little bit, like an increase in thermal energy means their temperature rises, but I can't convert that back into mechanical energy. A word that we use sometimes is dissipated. That energy has been dissipated into heat. It's no longer useful. Now, the difference with this stored potential energy is that it can convert back to useful mechanical energy, to kinetic, just by dropping it. And that's what makes this potential energy a stored form of mechanical energy. So how do we kind of quantify this relationship? So let me go back to the black. I know the blue's running out of ink a little bit. The amount of work done that goes into the stored energy, which we call UG, has to be related to how much work was done to lift that box at a minimum in a gravitational field. So if we look at this idea that the work done by the applied force has to be equal to FA times delta X, well, FA has to be equal and opposite to the weight of the object. Now, this is to not change the kinetic energy at all, just to lift it at a constant speed, the minimum force required. So, well, we know that Fg is just mg times delta X. And so the work done must be the force of gravity times the distance that the box is displaced. Well, now, since it's moving in the upward direction, we tend to call this delta y. And so this mg delta y is the amount of work that goes into raising a box a certain distance in a gravitational field. Well, that work now is useful stored energy. So we call that the increase in potential energy of the box. And really, this is the box-Earth system, because potential energy is a system property. It wouldn't exist without the Earth as well. So this is an increase in the potential energy of the box-Earth system. Now, there's a way that we can describe this relationship relative to the work done by gravity. So since the delta work was 0, the work done by the applied force plus the work done by gravity had to equal 0. Well, whatever this was the opposite in terms. So however much applied force work was done, the force of gravity did the negative amount, so that the total change was still 0. So we can say in this case that when gravity does negative work, the potential energy of the system with respect to the gravitational force increases by the same amount. So anytime something elevates in a gravitational field, that gravitational field is essentially storing up mechanical energy related to the height in the gravitational field and the weight of that object. Now, notice this is written as a delta. This is a relative value. We can pick the 0 point. Potential energy has significance in terms of its change in potential from one position to another, not the value of the absolute potential energy. There's really no such thing as the absolute potential energy. It's just how much has my potential energy changed in a system from one position to another. So this is another equation that we can add to our toolbox. And this is the calling card of a conservative force. A conservative force can store potential energy when work is done against it. We were going to see this pop up again when we look at springs. So springs are going to form a system. So when I compress a spring or stretch a spring, I'm storing potential energy. This is also a conserved quantity. And we're going to look into springs a little bit later on in the unit. But conservative forces are also associated with forms of mechanical energy. So we've learned already that mechanical energy is kinetic energy, energy of motion, and then potential energy, stored energy. And the two conservative forces that go into mechanical energy are the conservative force of gravity, stored in a gravitational field, and the conservative spring force, stored in what we call an ideal spring. I guess I should make that a little more specific. An ideal spring is one that doesn't deform when it's stretched or compressed. And these non-conservative forces, to kind of recap what happens with a non-conservative force. Non-conservative forces, so such as friction and drag, when they do work, they convert to thermal energy. So it's important to note, the energy doesn't go away. It just transfers or transforms into an unusable or a non-mechanically usable form, which is known as thermal energy or heat. And that's the difference between conservative and non-conservative forces.